Hi again. So, welcome to lecture one, part two. And in this part, we will continue to learn about some simple annotations. And also, we will learn some terminologies. Okay, let's start with a simple problem. Let's say you have a farmer and you specialize in raising wheat, corn, and sugar beets. And you have 500 acres of land. Okay, so you have to decide how much land to devote to each crop. And you are given some information, and you know that you will need 200 tons of wheat and 240 tons of corn are needed for the cattle feed. And these amounts, there's 200 tons and 240 tons, these amounts can be raised on the farm, or you can buy it from a wholesaler. So any production in excess of the feeding requirements will be sold. So what can you do, or how can you decide uh, to, to how much weight, corn, and sugar you will raise? Okay, you have to decide this. Or in this question, you will have to farm McDonald's. So the problem here is you don't know everything right now, right? So, for example, you are not sure about the yield of each crop per acre. So you don't know that. And this information is missing. Another important one is the feature, the wholesale price of wheat and corn. And you don't know if you don't raise them, you have to buy it, right? As I said before. But you don't know the future price of wheat and corn. So, and this is the second information is missing. Another one is future selling price of the wheat, corn, and beets. So, without this three information, it's not easy to make a decision, right? So, can you can provide some information to yourself. So in this kind of case, you may look at the history, and you can create some probabilistic model to describe some uncertain things. In our problem, the uncertain things is this information. So if you knew these informations, actually you don't need to use some probabilistic model. You can simply use some mathematical model, and you can solve this problem. Actually, this is after your graduation, this will be one of your main job, like we call it the operation research. And you can create some math model, and you can easily solve these questions. So you can maximize your benefits. But in this case, as I said before, we are missing, actually we have three missing information. And because of this, we have to create some probabilistic model by using some historical data. Okay, so that's why, as we mentioned in before, we have to use some probabilistic model to deal with the uncertainties. Okay, so actually I gave this this example just to make it more concrete between the relationship between the uncertainty and probability. So so we have to describe the uncertain situation with a math, right? So we need a mathematical description of an uncertain situation. So from this perspective, we have two main ingredients. The first one is the sample space, and which we will show the sample space by Greek letter, the capital Greek letter omega, right? So look, okay, I think it's right, omega. So simply the omega is the set of all possible outcomes of a random experiment. And also we will look at the term outcomes and the random experiments in a bit later. And then the second ingredient is the probability law. So this is simply a non-negative number, and we show it P of A, okay? And this is called the probability of A. So these numbers will be assigned to each element of the A, okay? So let me look at. Okay, so here, give me some simple example. Let's say you are tossing a coin, okay? So our sample space, the omega, is set of all possible outcomes, right? So let's say you are tossing a coin, and what is the all possible outcomes? So the all possible outcomes is the head and tail, right? So H and T. So this will be our omega, right? So this is our sample space, and the tossing a coin itself is a random experiment. So this is a fair coin, and just the tossing a coin is just a random experiment. So, and there are some probability, right? Like getting head or tail, and simply these are the mutually exclusive events, and these are the disjoints. So we can say this is a 1 over 2 and 1 over 2, and this is the P A, let's say, and this is the P B, right? And what is the A here? A is an event, and this event getting hat, right? Right? Getting hat. So, and this is a getting tail. So these are the events. So I think it's more concrete now. What's the sample space, probability law, and what's that? And the event, right? So let's continue. So if I need to give you more formal information, I can say that an underlying process, okay, called the random experiment. And in our example, the underlying process is tossing the coin, right? And that produces exactly one of the several possible outcomes. So in our example, the several possible outcomes stands for the head and tail. And at the end of the experiment, we get only one result, right? It is head or tail. So, and the set of all possible outcomes is called the sample space. It is a head or tail. But in our example, that consists of only two outcomes. But in some other problems, it may consist of finite or infinite number of elements. Okay, so let's say the examples. So like even digits, right? We show it. We saw it before. Like even positive digits. So it will start from 2, like, right? And 4, 6, 8. So we can extend this list infinitely, right? This is an infinite number of elements. And I say the sample space will be denoted by the capital omega. And also the subset of a sample space of the experiment is called the event. And in our example, the event is getting head or tail. Okay. So when the outcome of the experiment is observed in our example, we get the tail or head. And if the outcome is in A, we say that A has occurred. Okay, so this event is occurred. So let me show you the events in sample space visually. Let's say we have an experiment. This is our experiment, and what was the experiment we illustrated is the tossing a coin, or you can say like another the popular example in the probability lecture is rolling a die. But in any way, this is just a random experiment, and as a result of this experiment, we will get some outcomes, and these outcomes will create some events, right? Some events. Let's say this is a getting the head, and this is getting the tail, right? And then, based on the sample space and the events, we will calculate we will assign some probability, and this will create the probability of the events. Okay, so actually these events these events are actually the sets, right? So we have to deal with the sets, and we have to know some operations of the sets. Okay, so these are the simple things, but let me let me go over them just to improve your understanding. So let's say there's these are omega, and this is a sample space, and these are the events. The shaded region here, the shaded region here is the common region, right? So the common region between S, the event S, and the event T. So we call this part, okay? So S intersect with T because this is a common point. And now the shaded region cover all the events here, right? And we call it this S union. This is a T, right? Okay, this is a T. So this is an S union T. So let's look at the third example. In this case, we just shaded some part of S, like here, right? Some part of S. And there is something here. The points fall within the shaded region is not belong to T, right? Is not belong to T. And I can say that this is a T complement intersect with S, right? Because the T complement, the complement means the members is all the members not belong to T, right? Not belong to T. So all the points fall this region, and they are not the member of T. And the intersect with the S, that's mean among this region, what points fall within the S. This is this region, right? So I can mathematically write this. This is T complement intersect with S. So example D. So first, look at this one. T is is within the S, right? So that's why I can say that T is subset of S, right? So S covered T. And the points for these regions, okay, and they are not fall within, they are not member of the S and also not the T, right? So I can simply say that this is S complement, right? So S complement, again, the complement, what was the complement? The complement is the members not in S, okay? So this region. So let's look at the example E, and these three events have no common regions. And if this is the case, we call that these are the disjoint events, okay? Disjoints events, okay? And the last one is the S, T, and U create, or the union of them is the omega, and in this case I can say that the S, T, and U is the partition of the omega. Okay, this is the last example. So you can look at this simple notations just to make it better your understanding for the feature problems and for the feature topics. These are the simple things. Okay, so another one is the sequential models. So some experiments have an inherently sequential characters, like tossing a coin 3 times, like I toss 1, I toss 3, and I toss 2, and I toss 3. Okay, so I tossed the coin 3 times. So this is a sequential events. And another one is observing the value of the stock on 5 successive days. So this is a one event or one experiment. And receiving 8 successive digits at the communication receiver. In this time, I look at, or I received 8 successive digits, like a time series. Okay, so these are the sequential models. And if you have to deal with some sequential experiments or some sequential events, so you can use the tree-based sequential description. So let's look at the example. Let's say I have a 4-sided die and I will roll it 2 times. So this is a sequential experiment, right? And this part, this axis is the first roll and this axis is the second roll. So for example, this point show that in the first roll I got 3, and in the second roll I got 2. So let's create the tree. This is my starting point, and this part, like this, this part is my my first roll. Okay, so in my first roll I can get 4 different numbers, right? 1, 2, 3, and 4. So these are the possible outcomes of the first roll. And then in the second roll, this part is the second roll. For each possible outcomes, I can also get 4 different outcomes, right? 1, 2, 3, 4, and this will form the outcomes as 1, 1, 1, 2, 1, 3, 1, 4, and this one, in the case of getting 2 in the first roll, this will be 1. Oh, sorry. This one will be 2, 1, and 2, 2, 2, 3, and this will be 2 and 4. Okay, and same thing for the others. So if you need to deal with some sequential models, you can use the tree-based sequential description. Okay. So when you define your the sample space omega, and when it's chosen, it's time to introduce the probability law. You know the sample space, and then you can just you can create your probabilities. Okay, you can calculate them. So we specify the likelihood of any set of possible outcomes. Formally, the probability law assigns non-negative numbers, as we did in the tossing a coin examples. So that was the 1, 2, 2. This is a non-negative number. So this is the main rule. The P of A will be between 0 and 1. Okay, this is the unchangeable rule. And we call this the probability of A. So the probability, if you if you want to stand for the probability, it should satisfy 3 axioms. So you have to so I think not now. So the questions here, any function, any set function can be used for the probabilities, not, and it should satisfy the 3 axioms, and we will look at these 3 axioms. Okay. So to calculate the probabilities, actually there are 2 main categories. The first one is the frequency of the occurrence, and the second one is the subjective belief. Okay. So again, the probability is the concept for the uncertain situation. So that's not there is no something which is certain, right? So the first one, in the first option, we can calculate the probabilities by looking at the frequency of the occurrence. What I mean? Let's say I toss a coin again, and I did it like 1,000 times. Then I recorded my results, right? For example, in the first roll, first toss, let's say I get a hat, and in second I get hat, in third I get tail, and 4 I get hat, and 5 tail. So until the 1,000 times. So I can simply look at the frequencies. Let's say 501 times I get head, and 499 times I get tail. And by looking at the frequencies, I can calculate the probabilities. Okay, this is the first one, the frequency of the occurrence. So, and then the second one is the subjective beliefs. So one might think this is not interesting, but from the mathematical viewpoint or scientific viewpoint, but it's in sometimes, especially in the real life, you might maybe you need to use your subjective belief. Okay, so because why? There is no maybe the numerical historical data, or maybe this is a one-time event. And if this is the case, you have to your expertise, or you have to your belief. Okay, so this is the second one. And probably in I want to give you some examples to make it more understandable. Let's say we are we design a new product, and we will produce them, and we are not sure about the demand, right? So this is the unique product, and there is no any other example from another company. So we can just, and we don't have any numbers. So about the demand or some other things, just we know how and how much we can produce in a month, for example. So in this case, what you can do, you can use your expertise, okay, and you can use your belief just to plan your strategy, okay, or if you want to give a better decision, you can use your belief in the expertise in the market. So in this case, it's not possible to use any number, any frequency of the experience or another or other things. The only things you can use your expertise or your subjective beliefs. So that's why this is an important concept in terms of the probabilistic model